Hi, my name is Marcelo Iannuzzi, and in this lightning talk I will present BGP pass-state overlays as an alternative to BGP-SEC. First of all, let's try to understand what a pass-state overlay is, and to illustrate this, suppose that we have a set of routers that run standard BGP sessions. For them we have developed an overlay that provides specific control and management functionality. For instance, we have integrated array caches for origin validation purposes, and we have also developed what we call pass-state graphs. These graphs are distributed among autonomous systems in order to provide route validation through the overlay, offering a potential alternative to BGP-SEC. These are policy-shaped graphs that have very interesting properties. For instance, it can be proved that they are opaque in the sense that the policies enforced by domains cannot be inferred from the graphs distributed in the network. They can also help achieving much faster convergence and reducing churn. So in this context, one of the main questions is how do we make the BGP and overlay processes interoperate? To this, we have developed what we call the libPSP, which offers an API that basically supports the communication between BGP and the overlay. As you can see, we also support the communication among overlay entities located in different domains, in order to distribute information related to the pass-state graphs throughout the network. All this is supported by the pass-state protocol, which has two flavors: the external part that manages the communication between overlay entities in different domains, and the cross-layer part that enables interoperation with BGP. The value of this architecture resides mainly in the fact that PSP seamlessly enables the inspection and control of BGP updates, and also enables the construction, advertisement, and maintenance of the pass-state graphs of the network. All this packed in a way that may offer an alternative to BGP-SEC. So what about the libPSP? The key idea here is that only few changes were needed in BGP. Actually, only 88 lines of code were needed to make this possible. Another important fact is that it supports both active and passive modes. In this sense, the overlay could be inspecting without actually making any decision. For the demo that you will see in the next few minutes, we will show the use case of origin validation. For a video showing a route hijacking example, please visit our website at www.cracks.upc.edu/psp.html. In the example shown in the figure, let us consider a BGP update that is received by a standard BGP process that is only extended with the libPSP, that is, with the 88 lines of code mentioned before. The update is sent to the overlay process through the XPSP, where we have integrated the RTR lib, which is the one that actually enables the local cache for origin validation at the overlay. Through the RTR protocol, the overlay interacts with an array validator and with the RPKA infrastructure. Then the origin is validated by the PSP decision process, which is entirely performed at the overlay level, and through the XPSP, the message can be sent back to the BGP process. So as you can see, the overlay is actually inspecting and controlling BGP updates using a sort of man-in-the-middle approach. And the important part is that this can be used today with standard BGP4, since after the overlay inspection, we run the standard BGP flow including the BGP decision process, and if required, we can advertise the update to the neighbors. In summary, the overlay allows array offloading from BGP, and in fact in our implementation BGP is not even aware that its updates are being inspected. So let's now provide a brief description of the demo that you will see in a moment. As you can see, the topology is composed by 10 domains, 3 of which are located in Uruguay, like NIC, Antel, the national telco, and UDLR, the public university. 2 other points of presence include Cisco role in Switzerland, and all the brown nodes represent nodes in cracks in our premises in Barcelona. We also have an RTR server, which is the RTR validator for the nodes in the network, that is also located in our premises in cracks in Barcelona. For the software prototype, it is important to note that we have independent processes, the BGP daemon and the PSP daemon, both of which were embedded in this prototype in a Quagga router. There you can see the different ports that will be accessed, in particular the port that will be accessed during the CLI demo that you will see next. Another important fact is that the overlay can run a separate process on the same routed box or can use separate hardware. In theory, one overlay process could handle more than one BGP router. For the IP prefix hijacking example, what you will see is the following. In this network, the directed arrows represent customer-provider relationships, while the undirected ones represent peer-to-peer relationships. We will show that 5 will stream video that will be sent to 1 following this path in the figure, that is the path chosen by BGP. In that case, the video will be successfully received at AS1. After that, we will do the following. It will fake the origination of a prefix owned by 1 and will make the advertisement to its neighbors. And in that case, the possibility is that BGP follows this path and the hijacking attack can succeed. We will show the effect of this attack both with the overlay switched on and with the overlay switched off, and how the overlay can avoid entirely the attack. For the purpose of the demo, we use the RIPE ROS tool, and this is the route validation tool that we will use for all the domains. Let's now go to the demo. First of all, we connect to the overlay process running on the router in AX6. The overlay is supported by the PSP protocol, which from now on we'll simply call PSP. We enter into enable mode, and as it can be observed, the command line interface for the PSP is very much like commercially available CLIs. As an example, we show the PSP table from the command line, which, as mentioned earlier, is the internal representation of the policy-shaped graph constructed by AS6. Due to the tight agenda of this event, we cannot show the details and the benefits of the graph overlays in this short demo, so the people interested on an extended demo video involving the graphs and their applications, please visit our website at www.cracks.upc.edu/psp.html. Let's now show some administrative info, such as the PSP statistics summary. Through this command, we can observe the counters for the PSP messages processed by the overlay at AS6. At the moment, the overlay and BGP are running as two independent processes, since the communication between BGP and the PSP overlay has not been enabled yet, and that's why the ex-PSP counters are all 0. Let's now configure the RTR part of the PSP through the CLI. To this end, we need to set the RTR server, which in our case is Gandalf, a host located at our premises in Spain. From the PSP debug log, you can see that now the RTR functionality is enabled. Basically, these are the new entries that have been written in the ROA cache. For the purpose of this demo, these entries have been manually entered using RIPE's tool. To save time, we will now run a script to enable RTR in the rest of the nodes in the network. Let's now go to the standard BGP process running in the router in AX6, and let's observe its BGP routing table. The IP prefix that will be used for streaming the video is 66.89.5.0/24, and the path chosen by the router in AX6 to reach this prefix is AS10 AS1, so the initial data path for the video is 5, 6, 10, 1. Now we enable the overlay, which is done through the XPSP command at the BGP router. This command enables the seamless inspection of BGP messages through the overlay. We can confirm its status. It's idle because it takes a couple of seconds, but as you can see now, it is enabled. Again, to save time, we run a script to enable the overlay in the rest of the nodes in the network. It takes a while to establish all the connections and perform the configurations. After this brief introduction to the PSP command line, we have everything set to start with the IP prefix hijacking demo. Now we're going to stream a video from a source in AS5 to a destination IP in AS1. The sole purpose of using video streaming is to show the IP prefix hijacking case in a more visual manner. Then we'll falsely advertise the destination prefix through AS8, both in the presence and absence of the PSP overlay, to demonstrate prefix authentication by neither extending nor modifying the BGP functionality. And to make the attack more visible, in this demo, the video streaming will be hijacked and terminated at 8. But in a real scenario, AS8 could act as man in the middle by forwarding the traffic to AS1 transparently, so the application will not break at AS1. Now we'll run a script to start streaming the video. Recall that before the hijacking attempt, the video traffic follows the route 5, 6, 10, 1. As you can see, the video is correctly received at AS1. Before faking the prefix origination, we log in the router in AS8, and as it can be observed, the prefix that is to be falsely advertised, which is prefix 66.89.5.0/24, is already present in the BGP routing tables at AS8. Now we enter in configuration mode and fake the origination of that prefix. This is done using the BGP command line. After that, we can verify the result by looking at the BGP routing table at AS8 again. As you will see, the prefix is successfully advertised to its neighbors. However, the PSP overlay with the help of RTR is able to detect that this advertisement is incorrect, and the video streaming keeps getting received at AS1. This can be verified by logging in the router at AS6 and looking at the PSP statistics of AS6 for AS8. As it can be seen from the statistics, the increment in the modified and removed update counters shows that the fake advertisement was mitigated. In other words, the PSP overlay has suppressed this BGP update, so the video continues to be received by AS1. It is worth mentioning that these overlay actions are completely oblivious to BGP, so the BGP process is not even aware of them. Now, if we disable the PSP overlay, the fake advertisement by AS8 will be accepted by its neighbors. To achieve this, we only need a software start of BGP advertisements by AS8. After some time needed for the routes to be announced, the video will stop playing at AS1 and will start playing at AS8, demonstrating the successful hijacking of the video stream once the PSP overlay is disabled. In summary, we have demonstrated that our PSP overlay, endowed with the RTR functionality, can work in concert with current BGP4 to avoid IP prefix hijackings. So which are the hooks of our overlay? First, it enables non-disruptive inspection of BGP updates. In fact, only 88 lines of code were added to BGP, so PSP is compatible and interoperable with BGP4. Second, we have shown running code with a friendly CLI. Another important fact is that the information distributed through the overlay only contains data created, processed, and advertised by the overlay. For example, we do not trust BGP for constructing and maintaining the best state graphs of the network. The overlay also uses peer forwarding, meaning that the PSP avoids relying on the routing to convey information about the routing system we want to secure. In addition, it can be shown that, in accordance to compact routing theory, events can be optimally distributed through the overlay. Overall, the PSP overlay is an enabler for origin validation. Indeed, we have already integrated and demonstrated here the utilization of arrays in PSP, and path validation, which could be supported through the path state graphs, avoiding the need to sign every BGP update as in the case of BGP-SEC. Also, PSP dramatically reduces both the BGP convergence time and the churn rate of updates, which provides valuable credit for security overheads. It can also be shown that far less elements would be required for securing the routing system, since the number of overlay elements could be lower than the number of BGP routers. We would also like to especially thank to Ross White. Indeed, part of this work was done while Ross was at Cisco, like Nick, Carlos Martinez and Pablo Echeverria, Udelar, Eduardo Grampin for his valuable help, Antel Nicolás Antoniel and Pablo Cuello, and from Cisco Systems, Paramount Clues, Fred Baker, David Ward, Rodolfo Milito, Brian Weiss, Keyur Patel, Fabio Maino, Álvaro Retana, and Roque Galeano.